Hi, let's go ahead and finish up what we were talking about, binomial expansion and finding a specific term of an expansion. So, this is what I showed you guys last time, x plus y to the fourth. We saw all the sequences and all the patterns and how to put this stuff together, and we did a couple examples. But now, what if it was such a big expansion and we were just looking for a specific term, like x plus y to the 50th? Oh my word, I could do that, but I'd have to go down to the 50th row of Pascal's triangle just to get those numbers. Okay, so what we can do, there's a branch of mathematics called combinatorics that talks about what's called the counting principle and combinations and permutations, and it's used a lot in probabilities. But we can use this idea of combinatorics to find specific terms in Pascal's triangle. Like, I want to know what the 7th term of the 44th row is. We can use this combinatorics, this little formula I'm going to give you in a second, to find that specific term on Pascal's triangle. So let's go ahead and look at it. That's what we're going for. I'm going to give you guys some kind of expansion. Pink's not really showing up here. Let's try to make my room darker here. Nope, on that one. A little bit. We'll see. But finding specific terms of Pascal's triangle is what we're shooting for here. So here are some things. You'll see this on the internet in parentheses n comma r. This is what I usually use. Our book uses it. I've seen it on a calculator. I'll show you in a second. This one. Both of these will just be numbers, like 5, 2, 10, 1. Bigger number will always be on top, by the way. 10, C1, or 5, C2. And then inside of here is the actual formula. So these are the functions. You put these in your calculator, they'll kick out a number. This is what it's actually doing. You're going to have n, which is the power that I'm raising the entire binomial to. And then r is going to be the power of whatever the first term is. Because remember, when we're finding specific terms, it's always some coefficient. It's going to be the first term to some power. Then it's going to be the second term to some power. Okay? And we want n is going to be the power in our little formula here. N is the power that I'm trying to find of the whole thing. And then whatever these powers are, maybe this is a 5 and this is a 3. What I put here with a little smiley face is that it won't matter if you put in a 5 in your formula or you put a 3 in your formula, because of, if you can think about it, symmetry. If you think about the way Pascal's triangle works, there's symmetry going on with it. So if you plugged in one of them, you would get this. If you plugged in the other one, you would get this. And it's the same value, it's the same term, so it won't matter. We just have to pick either one of those once we figure out what they are. So we'll do one example here. Hopefully, maybe you don't know what factorial is, but factorial is multiplying a number by all the whole numbers, all the counting numbers before it. So if I wanted 5 factorial, well, it's a terrible exclamation point. 5 factorial is 5 times 4 times 3 times 2 times 1. And if you get into the fundamental counting principle, it talks about where this comes from and how we use it. But for our purposes, this is what we're talking about here. So it's basically a little formula that will help me find the coefficient. It will help me find that number that we're looking for on a specific term. Okay, let's do one example and call her good. I would like you to find the 4th term of the expansion of a plus 2b to the 8th power. Okay, without expanding it all the way. Ooh, that's a terrible expansion. Like, expansion. Perfect, much better now. So without expanding the whole thing out, we want to find that specific term. So we're already thinking it's going to be some coefficient. I'm just kind of laying it out there for you. If I was expanding it all the way, just to kind of show you guys some coefficient, the first term to the big power. First term to the big power. And then that one drops by 1 every time. And while that one drops by 1 every time, the other term, which is 2b, increases by 1 every time. So I didn't put it, but here's 2b to the 0, 2b to the 1, 2b to the 2, 2b to the 3. And this is the term I'm talking about. That is the 4th term in this expansion. The way I personally do this when they're worded like this, find the 4th term, you drop this number by 1, and that's what's going to go on our second term. Because remember, it starts at 0 every time and then increases by 1. So if I wanted the second term, then this would go to the first power. If I wanted the third term, it's to the second power. If I wanted the 8th term, it would be to the 7th power. So how I choose to think about this and help me fill out what goes on these powers right here is whatever term I'm looking for, do -1 from it, and that's what you're going to raise your second term to. Okay, if I'm raising this one to the third power, then I know this one, the one next to it, has to go to the fifth power because those powers will always add up to whatever our original power is. So this is what I'm looking at. I won't usually show this. Like if I'm doing a problem, I will go straight to this. This is what I'm trying to figure out, okay? So from here, we need to find that coefficient. So that's our formula we're talking about. N is 8 in this case because I'm raising the whole thing to the 8th power. R is either one of these, 3 or 5, 3 or 5. It won't matter because of symmetry, you'll get the same thing. So let's plug those in. Looks something like this. There's a formula, n factorial over n minus r factorial, r factorial. Okay, remember what factorials were? We just talked about that. We're multiplying 8 and all the counting numbers before it. So 8, 7, 6, 5, 4, 3, 2, 1. 8 minus 5 is 3, then a factorial. Okay, 3 factorial is 3, 2, and 1. And then a 5 factorial. A 5, 4, 3, 2, 1. Okay, a lot of this stuff melts away. You got 5 over 5, 4 over 4, 3 over 3. That all cancels. And then I can just simplify. How about a 3 times 2 on bottom is 6 with this 6. And I'm left with 8 times 7. 8 times 7 is 56. I can put this in my calculator, and depending on what calculators you have, we're trying to do 8 and 5. So 8, I go to the PRB for probability, because you use a lot of this in probability. It's NCR. There's the N and R we were just talking about with a combination, combinatrix. So 8C5. Hey, there's our 56. How about 8C3? Hey, 56. Because of symmetry on Pascal's triangle, it's the same number. Okay, so now we have what the coefficient is. That's what's going to go right here. We have a 56. A to the fifth, 2b, the quantity 2b to the third. Now don't forget, this coefficient is being raised to the third and being multiplied by this coefficient that we just found. So we were not quite out of the woods yet. This is what we have when we found the 56. I'll do 2 to the third. 2 to the third is 8. 8 times 56, 448. Then we have our a to the fifth, b to the third. That would be the fourth term of the sequence without having to expand this thing all the way. Okay, we're taking our little shortcuts with that. That's it. We've learned about expanding binomials. We can expand the entire thing. We can find specific terms of an expansion. Do those practice problems. Try the challenge problem. It takes a little bit of kind of combining the idea of sequences and patterns and then uses it with this idea of expansion. So it's a good little week for us. Almost done, you guys. All right, see ya.